Welcome. My name is Josh Hursey. Today I'm going to talk to you about the key value exchange modes in PMIx. I developed this talk with my colleague Dave Solt with valuable feedback from Ralph Castaigne. In PMIx, the primary means of exchanging data is via key value pairs. The key is always a string, while the value can be a wide range of different data types. There are two models for exchanging key value pairs, namely the process-related or process-associated key value exchange and the non-process related key value exchange. Today we're going to focus on the process-related key value exchange, which is probably the most widely used of the two. And maybe in a later talk we'll focus on the other model. There are four common patterns of process-related key value exchange listed here, really from the most heavy weight to the lightest weight. In the first pattern, a process would create a key value pair via put, make them accessible to other processes via commit, and then do a full exchange of all those key value pairs to all the nodes in kind of a heavyweight collective. And then all those processes can then access those key value pairs locally. That's probably the most traditional model when we start to think about these type of exchanges. Not all applications require the full set of key value pairs to be local, but do require some kind of synchronization between processes to know that they are ready to start wiring up together. Maybe the network is ready at that point to start connecting. So in the second pattern, we turn the collective operation into a barrier without the exchange, and then the data is pulled on demand during the get operation. Some applications don't even need the synchronization. So in PMIx, we've made the fence an optional part of the sequence. In the third pattern, processes proceed to the get operation immediately without a synchronization, and then data is pulled on demand as required to satisfy that operation. And then lastly, in environments that support instant on WireUp, all of the key value pair information that a process might need for WireUp that they would normally exchange is already available to them at startup. So there's no need for, so the get operation is satisfied out of the local cache and no exchange, synchronous or dynamic, is required in this particular case. One of the goals of PMIx was to eliminate the requirement for a synchronization operation during initialization and WireUp of the parallel library. With PMIx, libraries are allowed to synchronize, but they're not required to, and that frees them up to explore more flexible WireUp strategies. So as we previously touched on in the prior slide, there are four operations that when used together make up the process-related key value exchange: put, commit, fence, and get, each of which we'll discuss in more detail in the next few slides, so I won't dwell on them too much here. But I wanted to really identify three different WireUp models. Usually this type of key value exchange is used for wiring up processes during initialization so that they can begin to communicate. There are three different WireUp models frequently discussed with PMIx, and they're often referred to the PMIx community as a Modex or a module exchange, but more commonly they're known as a business card exchange. Though not the only use of this type of process-related key value exchange, it is a very common one, as I said. In the instant on case, the processes access pre-populated connectivity information from the Java level data available locally at startup, so there's no exchange in these environments. And this is a compelling model for environments that do support instant on. For those that don't, a direct Modex case is typically seen as the default in PMIx. In the direct Modex case, data is shared on demand based upon PMIx get operations between processes. Since the fence operation is optional in PMIx, that's why this is often seen as the default for PMIx. This type of Modex is useful for sparsely connected applications where processes may only access a small subset of keys from other processes, so they don't need everything, they just need a really small set. The full Modex case is, in the full Modex case, data is distributed during a collective operation between the commit and the get phases to cache all of the key value pairs local to the participating processes. This model allows processes to access information locally at the cost of a data exchange, resulting memory footprint. This type of Modex is useful for tightly connected applications where most of the processes access most or all of the keys from other processes. PMIx key value pairs can exist in a few different data realms. So asking for, say, the local set of processes means something different when talking about processes in the job versus processes on a single node. And so with a single attribute and the associated data realm, you can express quite a bit of what you're looking for. User-defined key value pairs using PMIx put are only associated with the process level data realm, while the PMIx server and host resource manager define the data in the rest of the realms. There are 5 data realms. The node level, these are key values associated with all the processes on the same node, possibly from different jobs. And then in the session level, are key value pairs associated with the set of resources allocated to this user. The job, or also known as namespace level, are key value pairs associated with the parallel job in the session, and there can be multiple jobs in the session, so it's good to distinguish those two. The application level are key value pairs associated with a group of processes within a job distinguished by the binary name, the argument set, or some other defined grouping. One example of this would be in an npmd launch, multiple binaries are used in the same job. Each set of binaries is an individual application in PMIx, though they all exist in the same job or namespace scope. And then finally, process level are key value pairs associated with this specific process. For this talk, we're primarily going to focus on that last data realm, though it's important to know that there are other data realms here in which these functions are used. For PMIx put operation, this prepares a key value pair to be shared within a specified scope. The caller's namespace and rank are automatically stored with the key value pair, so there's no need to encode that in the key anymore. It's automatically associated by the library in this packet. And so this is an important piece of information, the process rank and namespace. When the caller in the PMIx get is trying to access a key, they can say, give me this key from this process. And those are 2 different pieces of information, as we'll see. The key value pairs are not accessible until they're committed. And this allows a PMIx implementation to make the put operation really fast, as storing kind of just a local scratch space, potentially. The scope argument is important, particularly during the business card exchange, since some information, such as a local shared memory segment location, is only meaningful to other processes on the same node. So you'd use the PMIx local scope there. Whereas other information, such as, say, TCP or IP network addresses, is only meaningful to processes not on the same node. So you maybe use the PMIx remote scope here. Occasionally, a process will want to store a key value pair internally to the local PMIx client library cache for easier access later via PMIx get. If the information is about the caller process, then the caller could use PMIx put with the PMIx internal scope. If the information is about another process, since PMIx put associates the caller's namespace and rank, we needed a different operation for that. And so if you wanted to store information about another process, then the PMIx store internal operation can be used. And those are kept local to the client. In PMIx commit, this makes all of the previously staged key value pairs accessible to other processes. So as soon as the commit operation is finished, other processes can issue gets and access that data on demand. Those key value pairs with internal scope are not shared outside the caller, so they're kept in the client library. And those with the remote scope are usually pushed to the PMIx server and not accessible to the PMIx clients on the same node. During the commit call, the PMIx client will transmit the data to the PMIx server instance inside the resource manager daemon, the RM daemon. There's currently no up call into the RM daemon to let it know that this is happening, so the RM daemon is not interrupted here. During this exchange, the client and the server often coordinate to create a shared memory segment for the data to reside in to reduce the number of copies on the node, so not all processes need them, and then speed up access to that data by other clients on the node that may be accessing the same information. The PMIx fence operation is an optional part of the process-related key-value exchange, but one that applications and programming libraries often rely upon. In its default form, it's a collective barrier operation over the set of processes. Multiple fence operations can be ongoing, and the matching of those fences is determined by the order and content of the prox array. So that becomes our signature, our matching signature. If the caller desires a full Modex exchange to occur during the fence operation, they can pass the PMIx collect data attribute, which will turn the fence from, in MPI terms, MPI barrier into an MPI all-gather V. And the V is important because you have to remember that each process may be sharing a different amount of data in the exchange. And so it fundamentally changes the collective that is going on through the resource manager daemon. And that's an important thing to point out here. The PMIx library itself, the specification, is not intended to communicate off-node. It communicates locally between the PMIx client and the PMIx server, maybe locally with PMIx tools. But as soon as off-node communication needs to happen, an upcall happens into the RM daemon. So when a fence operation is requested by a PMIx client, there's an upcall into the resource manager daemon on the node to actually exchange the packet of information. The RM daemon will use its out-of-band network that it's set up to maintain its daemon set to perform the collective operation and return it to the PMIx server instance as efficiently as it's able to. The PMIx server will then make it available to the local clients, often by using a shared memory segment, which is a very efficient way to share and hold that data. Finally, PMIx get. So PMIx get operation is the means by which you access key value pairs in PMIx. The proc and info arguments determine which data realm that we talked about earlier that's accessing the data, from which you're accessing the data. If the key is a PMIx standard reserved key, which means that it's defined in the standard and it's prefixed with the PMIx dot set of characters, then the PMIx library looks to the local cache in the client for the data, and then the local server before returning an error. Reserved keys are established ahead of time by the local PMIx server, so there should be no need to look to a remote daemon for this information. That's why we just look locally here. The PMIx get refresh cache attribute that you see here requests that the PMIx server look for the latest version of the data before returning the key value pair. So it forces a cache refresh of the data before the key is returned. Now this is most helpful with user-defined key value pairs that change regularly, but sometimes reserved keys, the value behind them could change, particularly in dynamic applications. So it's important to point out here. For non-reserved keys, or often user-defined keys in PMIx, PMIx get behaves slightly differently. There's an additional step to the protocol here. It will still look in the client local cache before looking to the local server for the key value pair. If the key value pair is not available, then it'll issue a dmodex upcall into the resource manager to ask the target PMIx server for the information. Because remember, the PMIx server itself, that instance, cannot talk cross-node. So we have to make an upcall into the resource manager daemon to ask the other daemon to find the data for us and then return it. If the key is not at the target server, then the PMIx get operation will return a not found error. The caller local PMIx server, the PMIx server local to the caller, will likely cache the current set of committed values that were sent back from the other node so that if other clients try to request similar information, it can serve out of that cache without incurring another RPC call. If the PMIx required key attribute is passed, then if the key is not found at the target PMIx server, then the operation will block at the target server until either the key becomes available, meaning that it was committed by the target process, or a timeout has been reached. This is really often useful when accessing keys without that explicit synchronization between the clients, right? Without that synchronization, one client can get ahead and try to access connectivity from another process that's running a little bit slower. And in this case, we may want to actually block and wait for that to resolve before moving forward. Before we wrap up, I wanted to give an outline of the steps of the direct Modex operation, kind of in contrast with the full Modex operation. A direct Modex request is triggered when the PMIx call is issued on a key value pair about a process that is not already locally cached. Since the PMIx library doesn't communicate across nodes, it relies on the resource manager daemon to issue the request for the data and then route it back to the server. To do so, it roughly follows these 6 steps. So node 1, the resource manager gets the dmodex request up call, requesting the key value pairs for a particular process. Node 1 then determines that it needs to contact node 2, because maybe that's where that process is residing, and then sends a request over to node 2. Node 2 receives a request out of band from the resource manager daemon. It then calls into its local PMIx server library using the PMIx server dmodex request call. And this is really node 2's resource manager saying, give me the packet of information about this process. Once it has that packet, it'll then send it back to node 1. Node 1 will then feed that packet of data into the completion callback for the dmodex request, which feeds it into its local PMIx server library. That server library then will make it available to the PMIx clients. Usually this means that it'll store the information inside the shared memory segment and then notify the client that it's available there for it to access. And so a PMIx get call regarding a process may result in this RPC call sequence on that first access to that process. Once the committed data has been cached locally, then subsequent accesses to the key value set from that process should be faster since they're all served from that local cache. But that first call could be more involved. In contrast, the full Modex, the maybe more traditional mode that folks are familiar with, here the exchange of key value pairs occurs during the collective. So you incur the total cost during this collective operation and store that information in the shared memory segment. This results in a higher likelihood that the data is already cached at the cost of performing a larger collective and then having to store a lot more information on a single node potentially. So hopefully that gives you an overview of the process-related key value exchange semantics in PMIx. Clients first put data and then commit it to make sure it's available to others. Optionally, they can execute a fence operation to synchronize clients and exchange data, and then finally use PMIx get to access data either cached locally or on demand from a target server. The complexity of the semantics associated with these maybe seemingly straightforward tasks yields a great degree of flexibility for applications and programming libraries using PMIx and how they exchange key value pairs in the system. Thank you.